Good morning, everyone. And as I said, I'm Rohith Varikoti. I'm a data scientist here at PNNL. Today, I'm excited to share our research about an AI agent called CACTUS, which is an acronym for Chemistry Agent Connecting Tool Usage to Science. Uh, this is where we combine the LLMs with various open source tools to aid or assist us in various tasks, example as in drug discovery. Before moving forward with my presentation, I would like to acknowledge my team, the Cactus team, Neeraj, our PI, Andrew, Gautam, Carter, and Augustine. With Because of them, this wasn't possible. And I would like to thank US DOE Oscar, and LDRD, and Research Computing for the funding. And I would like to thank EMSL for giving me this opportunity. So going to a presentation, I would like to give a brief introduction for the LLMs. It's LLMs are nothing but advanced AI systems which are capable of understanding the human text, human prompts or human inputs, and generate human language like outputs. Most of them are based on transformer neural networks. Over here on your right, you can see just can you see my slides? Sorry. Yeah, transformer neural network model architecture. Laser pointer. Okay. This transformer follows an overall architecture using stacked self-attention layers and single point connected layers for both the encoder and decoders. And I would highly recommend or suggest you guys to look at the paper by Vishwani, which is titled "Attention is All You Need" if you want to have more detailed information or idea about the transformer neural networks. So these large language models learn various patterns in text using billions and billions of parameters to generate context-aware responses for humans to understand easily. And ChatGPT, you might have heard about like ChatGPT, Claude, Llamas are a few examples of the large language models. So how these large languages, LLMs, are used, or what are the applications of these LLMs. So we do have a huge amount of data available, uh, whether it may be the text data or the images or various voice uh, patterns or speech patterns, and various signals and information or output from various instruments that are uh, available for us. And this data is used to train a foundation model, which are like generic models that can be adapted to a wide variety of tasks, which may include, but not limited to, question answering, the chatbots that we see, sentimental analysis reviews and all, and extraction of information, and image captioning, as well as image generation. So we do have a wide variety of applications, but like how, as a scientist, how can I use these LLMs in science? So here is an example where we can use these LLMs to assist us in drug discovery. So LLMs can be potentially applied to various thrust areas or various areas, which include, but not limited to, therapeutic focus LLMs, where we can use these LLMs to predict the characteristics of a molecule, or identify the various descriptors of molecules, and also identify the genes associated with disease and so on. And drug discovery, where we can look at the target identification or prediction of various binding site residues, or lead optimization or QSR optimization, as well as designing a synthetic pathway for compound synthesis, as well as various other tasks include preclinical research, where we look at the toxicity, and clinical trials for forecasting various information, and so on. So Cactus falls into consider part of these top first three categories or tasks. So but we have this, but what is the main challenge we have right now? So there is like, how can we interface? Like we do have LLMs and we do have these open source tools free available, such as cheminformatics tools or bioinformatics tools that are available. And how can we build up an interface between them? And this is where our CACTUS comes into play. Here is a pretty much small example. How can we integrate the complex tools? As a chemist or a scientist, have an working on a example molecule, and he has an molecule. He or she has they have a molecule, and they want to know or learn more about that molecule. They can ask a question to CACTUS regarding that molecule, and our CACTUS gets an informed response of a particular question that you asked for. So here is the workflow for CACTUS. CACTUS, which utilizes a LangChain implementation of Miracle Agent, which is divided into, categorized into three parts. One is the LLM chain obtained from Hugging Face, and agent class, and the tools that we have available at to execute on the command. And or CACTUS follows a chain of thought reasoning method. A user has a question, and he asks a question to CACTUS. And the first step is that thought process, like or agent, the CACTUS or agent CACTUS looks at the question and thinks about the question and reads it and identifies what do we need or what the user needs. And then the second step goes into the action part. Okay, user needs a certain information. Okay, what's the best tool to have it, the question answered? Then it goes to the certain tool or the utilize the tool that's necessary and provides an feedback or output to the CACTUS. In the process, it looks at observes the output as well and check if the answer or output is correct or not, and then provides the feedback or the output to our agent, which provides an informed output to the user. So we have our agent and we have the large language model. So the motivation for use of these open source large language model for characters is to benchmark and evaluate the questions related to science we are interested in. And as of now, we don't have any benchmark data sets to evaluate and compare various models performance with related to science and specific tasks, domain specific tasks like chemistry or biology. So what we have done is we pulled a bunch of models from Hugging Face using LangChain and asked them same set of questions to all the models to benchmark them. Like over here, we looked at like models of different sizes to check how they perform on various hardwares, which I'll be discussing in the later slides. We use Llama 7 billion parameter models, as well as Mistral, Gemma, and Falcon 7 billion parameter model. As well as we have lower models like 5.2, 5.3, and Almo 1 billion parameter model. So one of our goal was to find the better performing model among these models for a specific kind of task. And once we find that model, we can fine tune that model for asking a specific type of questions so that the output or the informed output would be better compared to the individual model. And now we do have the LLMs and the agent. Now looking at the open source tools, we do have vast amount of cheminformatics tool. And if you have been used, like RDKit is one of the open source cheminformatics tool where you can use it using the Python. And SwissAdMe is another drug design tool, which gives us various descriptors or parameters based on the chemical structure or the input of a molecule. So we use these tools to integrate into our agent to get answers to the questions asked when the agent was asked. And we compare that to the ground truth values and to make sure the model is providing correct answer to the user. So how good our answers are compared to the ground truth values. This is what we looked into. And as I mentioned, one of our goal for this project is to provide a platform for open source scientific tools that are available and LLM models to get more informed answers specific to scientific sort of questions. Scientific questions related, it may be related to biology, chemistry, or okay, such that so we looked at like how efficient are these models when compared to API based models. Like we use the open source model and we compare that with the API based models, and also we looked at different what do you say hardwares, where how these model perform on a huge cluster and how they perform on a local machine. Are these models fast enough? And not only fast enough, are they accurate enough to provide a good answer to the user? So we use these all these to further so that we incorporate all these methods and tools so that this agent can be further used for various autonomous experimentation, or can be used for hypothesis generation, testing, and validation, giving or keeping human in the loop for trustworthiness. So we have all these made, like, and then what are the questions that are need to be asked? So okay. So this is how we benchmarked our various models. So we asked a set of cheminformatics questions. So we divided those questions into two sets. One is the quantitative set and the other one is the qualitative set. So we do have 10, as of now, we do have 10 tools available. And those are like divided into set of two. One is the quantitative and the other one is the qualitative. And we choose a set of questions like what's the molecular weight of caffeine example, and looked at the chemical formula of aspirin, or how similar are two structures. And we asked these questions to our agent CACTUS and looked at the answer. And we compared the answer, and if we get the exact or similar answer, we gave it an correct. And if our agent provided a negative answer or different answer, or if it didn't provide any answer, or it took a long time to answer, and we marked that as incorrect in our benchmarking sets. So we have done this with ask these questions to all the 7 billion parameter models. 7 billion parameter models, and uh, the smaller models as well. So these are the two types of questions we looked into. The one is a quantitative set where the response require an numerical response, which is like, for example, what's the molecular weight of a compound? Is it a float or an float value? And how many rotatable bonds that glucose have? It's an integer value. And we also looked at like the qualitative set where we asked like a descriptive answer or a Boolean answer. Like what is the gastrointestinal absorption of a chemical compound? Is it high or low? Is CCO drug like? Is a chemical compound drug like? Or what's the uh, does it pass the blood-brain barrier, yes or no? So we asked different types of questions. So what we have done for the benchmarking is that we randomly selected 100 smiles from the PubChem and asked 10 questions each. One is 5 quantitative and 5 qualitative, altogether 1,000 questions. And we worked with two different prompts. Uh, One is domain-specific prompt. We asked domain-specific questions. and one is the minimal prompt without just giving the user input, and checked how these two performed. So here is an example of Gemma 7 billion parameter model with a minimal prompt, which performed poorly for qualitative data set. Over here, you can see these are the uh, tools that are currently available. And these 7 billion parameter model with performed poorly in case of a generic or minimal prompt. But whereas going to the domain specific prompt, the accuracy or the performance of the model increased overall compared to that of generic prompt. And this shows that giving more and more domain specific prompt would result in higher, more correct answers, meaning more accuracy. So we have these for all these individual models and compare how they perform with the minimal prompt as well as the domain specific prompt. And since we want to compare all these models, so uh, we performed a model performance among all the 7 billion parameter models using minimal as well as domain specific prompts. So over here, we can see that the Gemma 7 billion parameter model, Llama, and as well as the Mistral model show robustness as well as versatility in the performance and having good accuracy compared to that of Falcon 7 billion parameter model, where it has shown a large disparity between. Over here you can see between the minimal as well as the domain specific prompts in almost all the questions. We observed that, and that disparity maybe can be reduced or by more fine tuning to improve models performance, as well as ask more uh, engineering, more domain specific questions and all. And then we looked at like how models can be served on variety of resources. How can we optimize the or CACTUS agent on various hardwares? So we deployed on different resources like based on GPU that we have used, the A100s, or the regular local machine, which is the RTX, which has an RTX 2080 titanium graphic cards, and we compare that with the APIs. And we looked at both the prompts. One is the minimal prompt as well as the domain specific prompt. And we looked at three sets of questions. One is the qualitative question and question set, and the other one is the quantitative set, and the other one is the combination of these both two as a full set. And we looked over here, we can see that Olmo, for example, smaller models like Olmo are performed poorly in presence of the minimal model, whereas the performance has been increased to more than 50% when using a full set and a domain-specific prompt. And moreover, domain-specific prompts over here achieved a higher level of accuracy compared to that of minimal prompts. And API, we have compared our models performance with the APIs, but like API has shown much more accuracy, but it takes long time, and due to quota limitations, we couldn't have with the full set as well as the quantitative set. So we have this, we compared, and we are currently trying to get more and more tools incorporated into our agents so that uh, it can be used on various tasks. So our future directions include development of self-optimizing algorithms, and we want to integrate more and more AI/ML-based surrogate models like graph neural networks and our 3D scaffold model, where we can use it to generate new compounds and then screen those compounds in complete using LLMs and our agents. And we also plan to include RL reinforcement learning algorithms to iteratively refine experimental parameters based on the outcomes that we get from those models. And the other step or the other major development we are working on is that integration of CACTUS agent into automated experimentation pipeline so that we can enable autonomous design and execution and analysis of the experiments as well as analysis of the output from various instruments as well. And and the third one is the expansion into diverse scientific domains where as of now, we currently focused on tools with respect to drug discovery, but right now, like we want to expand it to various material sciences and bioinformatics tools, and as well as catalysis, etc. And if you would like to learn more about the CACTUS, here's a paper which gives the detailed information of all the benchmarkings and all the models we have used. And here is a GitHub repo for our CACTUS, where we have the tutorials, and you can try it on Google Colab. I would be happy to share it, the tutorial right now. Sorry. Oh. Yeah. So here is the GitHub link. Here is a GitHub link uh, for our CACTUS. And if we go to the agent tutorials, we do have our various tutorials for different agents. And you can open in the collab. You can open it in the collab. Let me show you this, how it looks. We have the detailed information of the process, the architecture, as well as various tools that are available currently. And we do have how to set up our CACTUS using the various tokens. And we need, like, the first step involves installing dependencies where you will be installing, which will take a bit amount of time. And then this is a basic tool where we incorporate our CACTUS agent and ask a question, like we'll load our model. For example, over here, we have Gemini Pro model with the model type of API, and ask the question. So what, for example, what's the molecular weight of a given smiles notation? And this is a process that goes on, the thought process. Okay, I need to use the tool called calculate molecular weight for this given input. And it performs an action, calculate the molecular weight of that compound, and then observes the output, and then provides the output, like calculate the molecular weight of the given smiles is 180.06, etc. And here is a brief view of a tool that we use, where once we given the input to calculate molecular weight, it gets into the LangChain and uses the RDKit descriptors to calculate the molecular weight of the compound. And here are a few more examples and output from our CACTUS, and compared to that of ground truth examples, and how good these are. And we have few more examples of various medications as well as various dyes, and we use a different prompts to get the output and compare how good these are performing in compared to that of ground truth values. And also further more testing, we also looked into, like, okay, can it handle multiple questions? So what we have done is we asked like more than one question, like for example, what's the molecular weight of and log P of a given smiles, and does that trigger Brink filters, and does it pass the blood-brain barrier? So the agent first calculates the molecular weight using the molecular weight tool and provides you the answer observation, and then calculates the log P, and then the Brink filter and the blood-brain barrier permeability, and then provides the final answer, giving that the molecular weight of the compound is 180 and the log P is so and so, and the Brink filter, and it passes the blood-brain barrier. And the crown jewel of our thing is that we have generated multiple molecules that are not currently available in the literature, and these are completely novel. And we used our agent to calculate the properties and see how good are these compared to that of the ground truth values we got from the various resources. So it seems to be highly accurate, so that we can use this model to implement this model on the go and get the real-time data from the molecule generation into the screening process. And not only this, we have easiest way we can adapt is like we can integrate new tools. Sorry, we can integrate new tools into our CACTUS so that like you can adapt it to the problem that you have. And so feel free to contact me like if you have any questions, and I would like to thank you. Thanks. Oh, thanks everyone.
Thanks, Rohit. I think we might have time for a couple questions.
Sure.
Hi, great presentation.
Thank you.
And I have a question. I guess the input for CACTUS is the SMILE structure, like is the only input you can use, or maybe the name? Because I know the molecule can have different synonyms and that
Yes. So as of now, like our model is like has only input as a smiles, but now we are incorporating the Inchi key, Inchi, and the molecular formula and molecular formula as well.
Thank you.
Any other questions?
Thank you for the wonderful presentation. So I just have one question.
Yes.
So you said you used a lot of large language models from Hugging Face to
Yes.
build like a lang chain to kind of like build the cactus too. So I wanted to ask, like, what is the rationale behind selecting the large language models? Are they trained on chemistry literatures, articles or journals, or they are just like ordinary tests and then you fine tune to a particular database or stuff like that? So I really want to know how you selected those large language models and stuff like that.
So we selected these language models and train like fine tune that we want, like, since as I mentioned, we don't have any data of these application cases into the science. So we use that large language model and combined with the tools to get the answers that we needed. So these language models were chosen randomly, these were currently were available at that time, and we use those model to have it and incorporate into with our agent. And most of them don't have any may have information from various resources regarding the chemical structure or chemistry related, but we are training it to get more chemistry or domain prompt related, like domain related questions, chemistry in this case.